Hi, you guys. So this lesson is on section 4.2, which is on compound inequalities. So we're taking what we talked about in section 4.1, which was solving linear equalities in a single variable, and we're applying that to inequalities that are connected by either the word and or the word or. And thinking about like what those intervals, like what the solution set to those types of inequalities would look like what would those intervals of numbers look like. So for example, and this is not the only way that the solution to an and inequality or an or inequality could look, because remember, endpoints could be included or might not be included. So the situation that I've given us, or the inequalities that I've given us, neither of the endpoints of the intervals are included. So for x greater than a and x less than b, if we think about like graphically what that would look like on a number line, and let's assume that a and b, that a is less than b. So if I say this is the real number a and this is the real number b, for x to be greater than a would be, here maybe I'll use the highlighter, would be a would not be included, so I would use an open circle and then I would shade to the right of a for values that are greater than a, and x would be less than b. So for seeing what that would look like, here I'll use yellow. That would also be an open circle on the endpoint of b, but I would be shading to the left of b. And what this statement means is to be part of this inequality, or a value, a real number that when plugged in would make this statement true, the number would have to satisfy each of those inequalities. So x would have to be greater than a. At the same time, x would also have to be less than b. So the and is we're looking for the intersection of those two intervals, the intersection of x greater than a and x less than b, or like where they would overlap. So looking at this number line, we can see where the green and the yellow overlap is the intersection of those two intervals, which does not include the endpoints in this case. So another way that we could actually represent this same inequality is thinking x is greater than a and less than b. And this is kind of like the more compact notation. It means the exact same thing as x greater than a and x less than b. And sometimes there's reason it can be helpful to rewrite the and statement in this compact form, especially like if we're thinking about representing that same interval of values in interval notation. And then sometimes it can be useful to think about like separating the two inequalities. But we'll talk more about that as we go. And then for an or statement, an example of an or statement, let's take a look at what the graph, the number line would look like in this case. So again, A, then B. So for A, I'll use green again. For x less than A, so open circle on A because A is not included, and then shading all the values to the left of A. And then for x greater than B, open circle and all the values to the right. So what this statement is saying is to make this statement true, to be part of this interval of numbers, a real number must satisfy the statement x is less than a or x is greater than b. So if a number were to fall in either of those intervals, it would make the statement true because it's one or the other that the number would have to satisfy, versus whenever we have the and statement, both of those inequalities would have to be satisfied to be part of the interval of numbers that inequality represents, or the solution set to the inequality we refer to it as. So we introduced interval notation in the last class as another way to represent. We also talked about like the set notation, which was just basically taking the inequality notation and making it fancy with the curly brackets and saying X such that this inequality statement is true. Well, interval notation, whenever we are thinking about representing a compound inequality in interval notation, we think about replacing the word and with this kind of upside down U symbol, which represents or can be read as the intersection of the two intervals. And I use that terminology whenever I was describing the values that would be part of the solution set for that and inequality that we were just looking at. And then we can think of replacing an or with the union symbol here. So U for union. Okay. And the way that I think about it, so the intersection, it's wherever those intervals would overlap. The union, I always think of it as like the U, we're jumping over whatever interval would be between the two endpoints that are the endpoints of the intervals that are connected. And we think about writing our intervals, like we think about writing the endpoints, referencing a number line. So always thinking about reading from left to right. Now, the intersection, right, our and statement, can often be simplified to be written as a single interval. So in the example, we could see it up here, and it's easily seen in this more like compact notation for the inequality. But we could think about representing that same statement as just a single interval of numbers in the same way that we did for the compact inequality. Like just translating this and reading the number line, I would want to say that the solution set is the interval from A to B, like this, right? This would be the interval notation for that interval of numbers. Okay, another way to think about it is taking A to infinity, the intersection of A to infinity, and negative infinity to B. And infinity or negative infinity does not need to be included when we're talking about intersections of intervals, but I'm just going off of the example that I gave previously. And we can just think about, or it can be helpful to actually like draw it out on a number line, that this could be condensed into this simpler form of just describing as the interval of A to B. Whereas unions, you can't really simplify that more because the intervals do not overlap. And then I put a note here to pay attention to whether endpoints of intervals are included or not, and if you should be using a parentheses or a bracket. So remember parentheses to not include an endpoint as part of the interval or part of the solution set, and using a bracket to include an endpoint at the interval or as part of a solution set. So let's practice first looking at these different compound inequalities and kind of going thinking about, like, could we rewrite the inequality in a more compact form? What does the graph of the inequality look like on the number line? And then how could we write that same inequality statement in interval notation? Okay, so for x less than or equal to -3 or x greater than 2, that's an or statement, so I can't combine that into a more compact notation of the inequality notation. On my number line, I'm going to label as -3. I'll put 0 here. I'm trying to do kind of an accurate scale, right? Like I could think of that as being 1, -1, -2, -3. And then if you want to put values on the outside, right, like -4, and then that would be 3. So for x less than or equal to -3, -3 would be included, so I would use a solid dot. And then I would be shading to the left for values that are less than or equal to -3. And for x greater than 2, I would do an open circle and then be shading to the right. And I do think that graphing, at least at this point, for going from inequality to interval notation, I think reading the graph can be really helpful because you're always thinking for interval notation about your real number line and what values would be included as part of the solution set or part of the interval that's being described. So reading that number line from left to right, we would describe as -infinity to -3. -3 is included, but then notice that everything to the right of -3, like -2.9999999, is not included as part of this interval. So the way that we would exclude that interval directly to the right of -3 and then up to +2 is we put that union. 2 is not included, so we would use parentheses and then comma infinity, and we always use parentheses with -infinity and +infinity since they are not finite numbers. Okay, we have an and statement here. So thinking about this, we can condense this into a single, like a more compact inequality statement, which referencing our graph can also, like if you want to draw the graph of this, of these two intervals first, like that could also be helpful. But drawing our number line and then thinking about, okay, if this is -4, putting your values in order. Let's say that this is 0 and then 5 would be over here. So -4 is included and x is greater than -4. I'm going to draw each of those intervals. And then for x less than +5, 5 would not be included, and we would be shading to the left. So if we're thinking about, I'll use a brighter color here, where the overlap or where the intersection of the intervals is, it looks like from -4 up to 5, but not including at 5. So you can either you can reference your graph and go for interval notation directly to from -4 to +5. But I do think it can also be helpful to recognize that that's the same as saying the intersection, if you were to just read each of these inequalities, so the intersection of those two intervals. Okay, so that is the simpler form of that interval from -4 to 5. Okay, put one that's a little bit trickier here, kind of a trick question. So thinking about this one, let's look at the graph of the number line. So let's say that 0 is here and 6 is over here. Well, for x greater than 0 would be that interval. And then for 6, x greater than or equal to 6 would be that interval. So looking at what the intersection, because remember, and is an intersection of the intervals. Use a bright color here again. Right, that's saying from 0 to infinity intersects with 6 to infinity and 6 to infinity. The only intersection is the interval from 6 to infinity. If you look at that, right, that's where the two intervals would overlap. So this can actually condense just down to x greater than or equal to 6. Okay, and then this last one on this page, it's an and statement, an and inequality. So we can write this as x is greater than or equal to 7 and less than or equal to 12. Representing on the number line, we'd have from 7 to 12. Okay. And then thinking about, okay, 7's for x greater than 7 and x less than or equal to 12, that intersection of the intervals is between 7 and 12 and including those endpoints. Okay, so you could go directly to saying the interval from 7 to 12, or again, if we thought of this as the intersection of the interval from 7 to infinity and negative infinity to 12, that statement and interval notation can simplify down to 7 to 12 and including those endpoints. Okay, so this is to support us with representing our solution sets to these different linear inequalities. These are linear compound inequalities in interval notation as well. So notice here, though, that we have this and statement. We cannot, because we have nothing that matches, right? Like we have x plus 2 greater than or equal to 3. And then and 5x minus 1 is greater than or equal to 9. We could write that in the more compact form if it was like x plus 2 is greater than or equal to 3 and x plus 2 is less than or equal to 9 or something like that. But in this case, this is one we do have to work with them separately. So we can work with them separately in the same way that we did before. Make sure you are writing your and in between. So each line of work should be the same as the way that I'm showing work here. So this first inequality, I'm going to think about subtracting 2 from each side of the inequality by the addition property of an inequality. So that would be x is greater than or equal to 1 and adding 1 to each side of the inequality. So we get 5x is greater than or equal to 10. And then notice x greater than or equal to 1, we don't have any more work to do on. But over here at the 5x is greater than or equal to 10, we do have to think about dividing by 5 on each side of the inequality to get x is greater than or equal to 2. So at this point, you could rewrite this statement in the more compact form of the inequality. This is using inequality notation, referencing or representing this solution set graphically, right? Like you could think about, okay, if we have 1 and 2, like looking for the intersection, so x greater than or equal to 1 and x greater than, what happened? Oh, this doesn't make sense. Okay, so that's okay. We can fix this. Why don't we change this? Well, actually, no, we can make it work because so this would not actually be the intersection. Let's go off of this. So we can actually think of this as being x greater than or equal to 2. Okay, so then this can actually just simplify down. This is kind of one of those trick questions that I threw at you on the previous page. The overlap is only for x greater than or equal to 2. So interesting. I probably accidentally typed in the direction of the inequality wrong, but that's okay. We'll go with it. So like if we're talking about the intersection of the interval from 1 to infinity, and then 2 to infinity, that can simplify down to just be from 2 to infinity. Okay, so that's our interval notation. For representing the solution set to this compound inequality. Okay, so let's take a peek at this next one. So again, kind of working on each inequality that's part of the compound inequality separately. So we would have 3/8 x is less than or equal to -1 when we subtract 1 from each side of the inequality. And then we do have to think about when we divide by -2, we have to flip the inequality symbol. So getting x greater than 2. And the or ones especially, I do think it is helpful to reference the graphical representation. So thinking -1, 0, 1, 2. But, oh, I'm not done yet. Sorry. That's not what we're going to want to use. All right, let's think about multiplying. So you can either do it in 2 steps where you think about multiplying by 8 in each step. So that then you would have 3x is less than or equal to -8. But you could have also thought about multiplying by the reciprocal, 8/3 on each side of the inequality. Okay, so now we can actually, once we have x by itself on one side of the inequality, we can think about representing the solution set. So if we have -8/3, okay, which would be -2 1/3. So if this was 0, and then let's just say that this is 2. So x less than or equal to -8/3 would be that interval, and then x greater than 2 would be that interval. So now in interval notation, you can think about referencing your number line. So -infinity to -8/3 union 2 to infinity. Okay, and then one more. So in this first inequality, we would want to divide by -7 on each side of the inequality. So we need to remember to switch the direction of the inequality symbol. And then adding 20 to each side of the inequality. And this is an and statement if we think about rewriting this in the more compact form of the inequality. And then representing the solution set graphically. So 3, 4, 5. Okay, it looks like both endpoints are included. And this is one of for this one, I'm just going to reference the more compact form of the inequality, right? Because x is kind of sandwiched in between 3 and 5. You could do it from the other perspective of looking for the intersection, the overlap of the interval x greater than or equal to 3 and x less than or equal to 5, but it's really personal preference. Okay, so in interval notation, again, you can also just go directly to saying that that's equal to 3 to 5. It's also the intersection of the intervals 3 to infinity and -infinity to +5. So in the case that you are trying to come up with a solution set to the and inequality in its compact form, where you have kind of the x has to be uncovered. The goal is to get x isolated in the middle part of the inequality. So you have to remember that that statement represents two inequalities that are connected with the word and. So whatever you do to one part, you have to do to all three parts of the inequality for applying the multiplication or the addition property of inequalities. And you do need to remember whenever you multiply by a negative value or divide by a negative value, you have to switch the direction of the inequalities. So like for this one, we want to get x by itself in the middle of the inequality. So I would think about subtracting by 3 on each part to get -2. We still have negative x in the middle. And then 5 is kind of the upper bound there. And then when we think about dividing by -1 or multiplying by -1, we do have to remember to switch the inequality, the direction of the inequality symbols. And now this is kind of a funky way to read that. So I would switch the order here to match up with the order of a number line, especially then if you're going to graph that inequality on a number line. So -5, let's say 0 is here, so 2 would be about here. So -5 is not included, 2 is included, and we would be shading in between. And then in interval notation, we can just go directly to describing that interval as the interval from -5 to 2. We use the parentheses for -5 because -5 is not included in the interval. And we use the bracket with 2 because 2 is included. Okay, for this one, we are trying to get to that x. So we can think about multiplying by 4 on each part of the interval. Then adding 1, and then dividing by 3. I'm okay showing dividing by 3 here. You do want to be careful that you don't accidentally make a false statement while you are trying to go through the process of isolating x. Even if like you do end up with the correct inequality at the end, you cannot make a false statement in the middle of your work. So if I was dividing by -3, I would be writing that as another step where I have shown that I have switched the inequalities. So what is that? -13. X is greater than -13 and less than 7. Okay, so thinking about our number line. So -13, say 0's over here and 7's here. So open circle on both -13 and 7. And these and statements we end up shading in between. Okay, and in interval notation, we can just reference our number line or our inequality from left to right. So -13 with parentheses to 7 parentheses because neither endpoint is included as part of the solution set. Meaning, if we plug either of those values in for x, we would get a false statement. Okay, and then the last one here, we could think about if you can leave the decimals, or you could always think if I multiply each part by 10, I would have -7 is less than or equal to 4x plus 8. Oops. And 4x plus 8 is less than 5. So now I can deal with integers and subtracting by 8 on each side. You didn't have to do that step, but you could. Okay, and then subtracting 8 from 5 we would get negative 3, and then our last step to divide by 4. So negative 15 fourths is less than or equal to x, and x is less than negative 3 fourths. Okay, so to draw our number line, so negative 4 fifteenths would be negative 3 3/4. Oops. So negative, I'm just going to draw negative 15 fourths. Negative 3 3/4, let's say that this is 0, and then the negative 3/4 would be a lot closer. Oh no, that's not 0. So negative 3/4 is going to be closer to 0. Okay, one endpoint is included, the other is not included in this case. In an interval notation, that would be bracket negative 15 fourths to negative 3/4 parentheses. Okay, so representing, finding the solution sets to these different compound inequalities, and then also representing those solution sets in interval notation.